Good morning. Now we will discuss about the nodal analysis, the different method for solving electrical circuits. In today's class, we will discuss the steps that will be involved that we are supposed to follow for simplifying or analyzing a circuit using nodal analysis. In the last lecture, we have seen numerical problems on mesh analysis. I think we have done nearly 4 to 5 problems on mesh analysis, and I hope that you are well acquainted with the mesh analysis. In today's class, after the completion of today's class, I hope that you will be able to describe the steps that are involved in nodal analysis. In mesh analysis, we have gone for 6 steps. So in nodal analysis, we will see any similar number of steps, 5 or 6 steps we will see, and you should be able to describe those steps by the end of this lecture. So I'll start with the why nodal analysis and then the steps involved, and we will try to solve a simple problem on nodal analysis. So just like your mesh analysis, nodal analysis is also used to analyze electrical circuits. Your mesh analysis was dependent on KVL, right? Kirchhoff's voltage. Whereas nodal analysis is based on Kirchhoff's current law. The Kirchhoff's current law, you know that sigma I is equal to 0 at any node in a circuit. So it states that the sum of currents entering a node must be equal to the sum of currents leaving that node, or we call it as algebraic sum of the currents at any node in an electrical circuit is 0. And nodal analysis is a powerful technique generally employed besides your mesh analysis. Normally in electrical circuits, particularly to determine the nodal currents or the branch currents, particularly the branch currents and branch voltage and node voltages, we will employ this nodal analysis. In this one, we will identify, first of all, we will identify the nodes in the circuits, and then we will assign them some voltages. And then we determine those voltages using KCL equations. On all these equations, they will be written in terms of voltages and the resistances, and if at all, if there are any current sources, they will be also written in these equations. So when we try solve all these equations, we will get the voltage at each node, and from that we will determine the currents and powers in various branches. So these are the steps which I have written for you for determining the branch currents and voltages or simplifying a circuit using nodal analysis. See, the first step is you are supposed to identify the number of effective nodes in the circuit. See, a node is a point in an electrical circuit where more than 2 elements are connected. So first of all, you identify the nodes. Okay, then you identify the effective nodes. Okay, that I will teach you when we are doing in the problem. Okay, so first of all, you identify where the points where 2 or more elements are connected, and then you assign 0 volts for any of the nodes. This is called as a reference point. This is mandatory in nodal analysis. You are supposed to identify one reference node and assign 0 volts for that. And once reference node is identified and 0 volts is assigned, the voltage at other nodes based on the voltage sources that must be identified. If that is not available, then you should assign some voltages. Let us suppose if there are 5 nodes, 1, 2, 3, 4, 5. One of it will be assigned 0. And for the rest of these things, if you do have voltage sources, then you give it as like this. If you don't know them, then you assign it as V1, V2, V3 like this. Understood? This is what I said. For reference node, you assign 0. Choice of reference node is completely yes. And then, if you do have any voltage sources, identify the voltage at that particular node based upon the voltage sources. If not available, then you assign voltages. Okay. So once this step is done, you apply KCL for each of these effective nodes. Effective node is one which voltage is assigned. Just like your V1, V2, etc. Those nodes are called as effective nodes now. So for that nodes, you are supposed to apply KCL. When you are applying KCL at that particular node in nodal analysis, you should ensure that this is the most important. The node you are considering is leading, and all the currents are going outwards from the nodes. Okay, so sum of currents. So you assume that all the currents are leaving that node, and you consider the algebraic sum of those leaving currents is 0. So how to determine the currents? If you do have directly I, it is okay. If not, voltage drop by resistor. Either of these things is okay. So based upon that, you will be writing equations at all the effective nodes. Once you do get those equations, you determine the nodal voltage by solving the equations. And finally, you determine the branch element or currents. Okay. So a simple steps. I'll start with identifying the number of nodes and then assigning them voltages and then applying KCL and then solving those equations and finally determining what is required. Okay. So there are few limitations. The first biggest thing is it cannot be suitably applied with networks for dependent sources. And second thing is it requires a reference node defaultly. Selection of reference node may vary the complexity of the problem. So that must be taken care of. And also, as the number of nodes increases, the number of equations will also increase, which makes it a little bit complex while we are solving the problem. Okay. So now we will try to apply those 5 steps for a simple circuit. Okay. So let's try the problem on nodal analysis. We'll try this one. See, this is a circuit which has been given for you. You are supposed to determine the voltage at each of these nodes of the given circuit using nodal analysis. Okay. So when I'm asking you this one, the first thing which you should remember is the 5 steps which I have already told you. So if you see this circuit, if you see these particular circuits, now how many nodes are there? This is anything where 2 or more elements are connected. It is called as a node. So this is one node. This is second one. Right, because here 1, 2, 3 elements are connected. Here 1, 2, 3, and here see this is completely a single node. This element is connected, this element is connected, this element is connected. So I'll directly take it as 3. And here see there are 2 elements connected here. It is 4. The same I have mentioned here. So totally how many nodes are there? 4 nodes are there, and they have been assigned 1, 2, 3, 4. This is step number 1. And coming to step number 2, once see this is 1, this is 2, and this is completely 3, and this is 4. Once it is assigned, now what we should do? We should assign voltage for that one. So one of these should be given 0 volts. So I am taking this one as 0. Preferably I take the bottom one as 0. Okay, so 0. Once it is 0, see you identify the voltage at the remaining nodes. Since this is 0, see this point is at 0 and this point is also at 0. So if it is 0, see if I move from here, this point is at 100 volts above this one. So at 4, I defaultly have 100 volts. Understand? Because what is the difference between this 4 and 3? There is a 100 volts voltage source, which means that if 3 is 0, 4 is at 100. Whereas for at node 1, I can't identify because I don't know what is the voltage drop here. So I'll take it as V1. Here I'll take it as V2. So this is the way how I have assigned. See, for 3 I have taken as 0 volts. For this one I have taken as 100 volts. And for this one I have taken as V1 and this is V2. This is step number 2. I'll repeat it again for you. Bottom one I am taking as 0. And here this one I am taking it as 100 because there is a voltage source between them. And the remaining I don't have any particular clarification, so I am taking as V1 and V2. Once I do get these things, I'll write KCL equations now. See, this is 100, right? This is 0, this is also 0, and this is V1, and this is also V2, right? So now I will start writing KCL for each of these effective nodes. So this is node number 1. So at node number 1, how many paths I do have? 1, 2, and 3. So this is path number 1, path number 2, and path number 3. I'll take that. All my currents are going outwards. This is the fundamental thing which I have told you. So 3 paths are there. So I'll take 1, 2, and 3. So what is the first path? Correct. It is starting from here and leaving to here, right? So do I have any directly voltage here, sorry, current here? No, current is not mentioned. So what options if I do have? Either if you have current I, you will take I, otherwise V by R. Voltage drop by R. What is the voltage drop here? From here, V1 minus 100 by, what is the resistance? 5 plus path number 2. Voltage drop is V1 minus 0 by 30. Next, this is V1 minus V2 by 10. Right, this is the equation which I mentioned here. You take the LCM. What is the LCM here? 30 is the LCM. You solve it, you will get this equation. This is my equation number 1. Similarly, at node number 2, if you carefully see, this is node number 2. How many paths do you have? 1, 2, and 3. Right, this is V2, this is V1, and this is 0, and this is also 0, right? So, how many paths I do have? 3 paths. 1, 2, and 3 combinedly 0. So, in this path, what is the current? V2 minus V1 by 10 plus V2 minus 0 by 10. Right, next V2 minus 0 by, what is this resistance? It is 20, right? V2 minus 0 by 20. You take LCM, you solve it. This is my second equation. Now I do have two equations now. You solve these two equations, you will get V2 and also V1. So which means that this is at 27.27 volts and this is at 68.18 volts. Understood. So the problem is solved. Step number 5, no need, because my question is determine the voltage at each node, and it is solved now. Okay. So this is the way how we try to apply nodal analysis for analyzing a circuit. I hope that now you are able to describe the steps. So a quick review. Step number 1 is you identify the nodes. Step number 2, assign them voltages. Step number 3, apply KCL. Step number 4, solve the equations. Step number 5, determine the responses. Okay, so 5 steps. I hope that you practice them. Try to solve this particular problem at home, and we will solve more problems in the class. Okay, thank you.